Expressions involving trigonometric functions and their inverses arise in different areas of mathematics. One such example is in the fundamental theorem of calculus. In the next few examples, we'll go ahead and illustrate how to simplify and evaluate these types of expressions. Before we do that, let's go ahead and recall how we can represent inverse trig functions as a triangle whose sides represent different x expressions. We'll review this derivation for sine x, and then we'll just list what it was for cosine and tan. Suppose we begin with our sine inverse of x, and this is equal to y. Again, by definition of an inverse function, this gives us x is equal to sine of y. And we can represent this as a right triangle, where the angle is given by y, and sine of y is represented by opposite divided by hypotenuse. Therefore, this will give us x. This will be 1. And the remaining side is given by the square root of 1 minus x squared. So we'll go ahead now and list the associated triangle with tan inverse and cosine inverse. We'll go ahead and use each of these in the next few problems where appropriate. So let's go ahead and look at an example. Here we want to write tan evaluated at sine inverse of x plus cosine inverse of y in terms of x and y. First, set theta is equal to sine inverse of x, and set gamma to be equal to cosine inverse of y. Now draw the associated right triangle to each of these inverse trig functions that we did in the last slide. And recall that this is going to allow us to evaluate trig functions where we evaluate at theta or gamma. And what we want to do now is we want to replace our sine inverse of x and our cosine inverse of y with theta and gamma respectively in our tan. So let's go ahead and first rewrite tan as tan evaluated at theta plus gamma. And now we can go ahead and use our addition formula. Then this is going to be equal to tan theta plus tan gamma divided by 1 minus tan theta times tan gamma. Now we can evaluate tan theta using this right triangle, and we can evaluate tan gamma by using this right triangle. So tan theta is going to be equal to x divided by the square root of 1 minus x squared, and tan gamma is going to be equal to the square root of 1 minus y squared divided by y. So I'm missing a y squared there. So plugging this in to our equation on the right-hand side, we'll get that this is going to be equal to x divided by the square root of 1 minus x squared plus the square root of 1 minus y squared divided by y, divided by 1 minus our x divided by the square root of 1 minus x squared times the square root of 1 minus y squared divided by y. Let's go ahead and simplify the answer that we just obtained so that we get rid of all fractions that we can and the square roots from the denominators. So combining the fractions up top and combining the fractions on the bottom, we should get that this is going to be equal to the following. We see that this and this cancels out, and we're left with that this is going to be equal to the following. And we're done. So really, either this solution would work or this one over here as their equivalent. Let's look at one more example. If we want to find the exact value of sine evaluated at these inverse trig functions. Again, we can go ahead and just set theta to be equal to cosine inverse of 1/2 and construct a right triangle associated with this. So this is a right triangle whose angle is theta, whose adjacent side is 1, and whose hypotenuse is 2. Since this is a right triangle and we know two sides, the remaining side is going to be the square root of 3, which means this is a 30, 60, 90 triangle, and theta is equal to 60 degrees. Now set gamma to be equal to tan inverse of 1 and construct the right triangle. So this right triangle is going to have opposite side 1, adjacent side 1, and this is our gamma here. So the hypotenuse has length square root of 2, and this means that gamma is equal to 45 degrees. Therefore, we have that our sine can be represented as theta plus gamma, and this is equal to sine evaluated at 60 degrees plus 45 degrees. Now, rewriting this using our sum formula, this is going to be equal to sine of 60 degrees times cosine of 45 degrees plus cosine of 60 degrees times sine of 45 degrees. Now, evaluating this, we're going to get the following. Simplifying this, we see that this is going to be equal to the square root of 3 times the square root of 2 divided by 4 plus the square root of 2 divided by 4. So we're going to get that this is going to be the square root of 6 plus the square root of 2 divided by 4.